Hey everyone, this is Kishloy, and in this video, I'm going to talk about a particular aspect of marketing mix modeling and perhaps regression and analytics in general that I think deserves far more attention than it gets. And this is the concept of signal to noise ratio. So, as you can see in this document in front of you, this is what it talks about. But before we jump into the ratio itself, let's actually talk about these two terms that have come up: signal and noise. So the signal is nothing but actually the effect of a particular channel. Okay, and by that effect, again, effect itself is also a term in this space, and that means simply the contribution to the revenue a particular channel has, or depending on what is the level of analysis in your model. That of course, so this of course, the effect of course means therefore the effect of that level of analysis. So if it's a campaign level analysis that you're doing, so the effect of a campaign, or if it's a channel level, then it's an effect of a channel, so on and so forth. So that is simply the definition of signal. We're going to see the mathematical aspect of it, just a brief understanding of the maths behind it. Next, we can move on to noise. So, noise is nothing but residuals. It's the errors that remain after accounting for the effect or the contribution of all the channels, or like I said, the other level of analysis, if any. So, this basically means, therefore, unexplained variance. So, that is basically your noise. So, the ratio of these two, essentially, you can say that that gives you the signal to noise ratio, and this is actually the mathematical form of it, this formula here, which gives you the variance. So this SNR, the signal to noise ratio, is given by the variance of the effect or the contribution, which is given by um, the estimated beta hat, which is basically your coefficient for the specific channel X. And then you also have, and you take the ratio over the variance of the residual, or the square of the standard deviation, which is the variance of the residual, and that was the predicted value. So the hat stands for those. So this is basically what gives you your standard sorry, your signal to noise ratio. Now that's fine, but why is it important? Now it's important because this actually gives you a very nice understanding of model fit relationship, and nothing explains it better. We're going to actually look at the mathematical derivation of it in a moment, but nothing explains it better actually than this chart itself. You can see that we have, on the x-axis, we have the r squared, or the coefficient of determination, as you would know, which gives you the the level to which the model has been explained by your regressors, or by your predictors in the model, and therefore a good measure of model fit. And on the y-axis, you have your signal to noise ratio, which is given by r squared by 1 minus r squared. So we're going to come to the derivation in a moment, but from this graph itself, as you can see, we have four different parts here. This part here, if I just zoom in a little bit, you'll see this is the low SNR part, which is the noisy part. Let's see that first. Like, it's at 0.2 r squared, which of course is very bad r squared, but it also has low signal to noise ratio. So this means that the higher the signal to noise ratio, the higher is actually going to be your r square. So this is a directly proportional relationship. So as r square increases, SNR also increases, because that's actually given by the formula itself. But if you could have also exchanged axis as well. Like, you could have had SNR here and r squared here, but it would have looked just the same, because if SNR increases, r square also increases, so they are exchangeable across the axis. And you can see that this is the point of equal signal noise, which means that SNR is equal to 1, right? So this basically means that your r squared is zero point 0.5. If you actually just replace zero point 0.5 in this formula here, you will see that this is what it comes to be, which is signal to noise ratio of 1. So this is actually, you can say, the basic threshold of a model, right? So if you have an SNR which is just 1, this means that you're going to get a like 50% level of significance. You can say, in a sense, I mean, it's not exactly level of significance, but you can say that it's that level of model fit, which means that your signal is actually just exactly equal to the amount of error that is getting generated by the model. So this is the bare minimum, and this is kind of like a break even. but a good fit starts happening when SNR is actually greater than 1. So this is where it's 3 times more than 1. This is at 3, and you can see that it corresponds to an R squared of somewhere between zero point 0.7 and zero point 0.8. Now you can see that this is not a linear relationship, right? You can already see because it's a quadratic relationship, which is why you get this sort of a curve here. And then you obviously have even better SNR corresponding with even higher R squared. So actually, as you get closer and closer, so for these values here, like you will have to have really steeply increasing SNR values for any higher R squared. Okay, I mean that would be even clearer if you just exchange the axis here. But either way, you can understand that this jump here, as you can see, from getting from say 0.75 to zero point 0.9, you had to jump a massive amount by 6 times, from SNR of 3 to SNR of over 18, like that's 19. So this is that's the non-linear nature of the relationship. So as the model gets better and better, you need to have really really high quality signal to noise ratio, which simply means having better quality data, or better, or simply more data. Now this proof here for this relationship that we have actually used in this graph, which is R squared by 1 minus R squared being the signal to noise ratio, is taken from this particular resource, stat proof book, on github.io. Do check it out. It's an excellent resource, not just this page but this entire stat proof book website. So now let's look at this, and so I'm just reproducing the proof from there. It's very nicely done. So we start with the basic assumptions of our our stylized model, where we get a very standardized model, a standard model rather. So y is x beta plus epsilon. So we have taken just as one channel here. Of course, this could be any number of channels, and where we have the error also, which is normally distributed with 0 and sigma square as its parameters, is mean and variance. So that's basically a very normal linear model definition. And you have the OLS estimator. So the beta hat predicted coefficient is given by this expression here, which we are very familiar with if you're familiar with the linear algebra matrix representation of regression model. So based on that, now we can actually come to, I will suggest that you actually look at this line here. This is basically a very important property of linear regression, where the variance is actually split up. The variance of y, the predicted value, is split up between the predicted value of the variance of the observed variables, actually given by the summation of the variance of predicted value of the variable output variable, and the variance of the residual. So that relationship is actually what is also getting used here. So the SNR is, by definition, we know that is the variance of the predicted value of the output variable and the variance of residual. That's its definition, right? Um, that's how it's defined, signal to noise. And then it gets split up. As you can see, you can write this predicted hat here in the form of the variance of y minus the variance of the residual, which is why you get this numerator here. And so from there you can see the R squared is given actually in this form. Again, this is the definition of it, where you have 1 minus variance of epsilon by 1 minus variance of y. And this is again given by this relationship once more. And once you use that, you can actually rearrange it finally to get SNR R squared minus 1 minus R squared. Now the question here is, what's really the core issue here? Why are we even discussing this? A major reason why we discuss this is because we often see that I have seen this during execution of projects, that when you have a lot of channels, the smaller channels kind of get submerged, you can say, or they kind of get overwhelmed by the amount of noise that's getting generated in the model, because they just have such low levels of signal. But at what point does it really start becoming a problem? There are lots of thumb rules, with respect to, say, coefficient of variation, like what should be the relationship between sigma and the standard deviation. So all those things are there, but this is a very nice mathematical way also of looking at the overall models situation, so that you can understand whether or not small channels will actually make sense, and we're going to be able to sort of analyze them. So let's look at a simple example. Suppose you have an average weekly sales of say $500,000, and a residual noise, which is after the modeling, comes to around say plus minus $50,000 per week. Okay, so that's your like your standard deviation. And now you have two channels, large channel TV. Suppose, like I was saying, so it's a mix of larger and smaller channels. So you have say $100,000 per week of spend, and it drives it $200,000 in sales, go with an ROI of 2. But the smaller channel, like say podcast, you only have say 5,000 per week of spend, and it drives say $10,000 in sales. So you can see that this amount is much smaller, and it's actually much smaller than the residual noise. So both channels face the same noise. So the noise is the overall noise that's getting generated from the channel. As you can see here, it's written, it's not the noise from the larger channel that matters, it's the noise that gets generated from the overall model. And therefore, even though they face the same noise, but the signal to noise ratio is simply the signal divided by the noise. So you have 200 divided by that 50k noise, you have a SNR of 4. But in the case of the podcast, it's 10 divided by that 50, which is just zero point 0.2. So you can see that this one is going to get swamped by the noise, the smaller channel. And this is typically what happens here in marketing mix modeling. And we have to understand that this does not necessarily come from the larger channel. So this is why it's important to understand that it's not necessarily the case that you have some channels which are getting over attributed. Necessarily, it could be, of course, because of improper model specifications, like it's been mentioned here, like maybe say wrong functional forms, maybe you have used at stock functions which are resulting in over attribution to certain bigger channels. But in most cases it will also be say unmodeled factors, I'll say, like seasonality or competitors or macro trends or whether you might be missing out. So there's going to be omitted variable bias that might actually creep into the model. In most cases I've seen that's the reason. But yes, there could be some other errors or say misspecifications which can actually lead to this. And you'll see that there's also this chart here which actually gives you like what's going to be the level of minimum detectable ROAS that's going to be useful for the different kinds of channels depending on the amount of SNR they have. So for larger channels, as you can see, they have high weekly variance, and therefore signal is going to be much more than noise, and therefore the minimum detectable ROAS is much lesser. So you basically need much higher minimum detectable ROAS. Why we are saying that? By the way, this is after the modeling part. We mean like the actual ROAS of the channel. They don't need to have very high ROAS if the channel is much bigger and they have higher weekly spend. But for smaller channels with lower weekly spend and they have lower variance as well, you need much higher minimum detectable ROAS. Otherwise, the signal is going to be because it's going to be really getting swamped by the noise. So what does it so one of the things that we talked about is the relationship of SNR with model fit, but there's also the important aspect of the relationship with data requirements. Like, so how do we deal with it, right? So how do we ensure that we don't have a very low SNR and the channels don't get underrepresented or misrepresented because of this? So a good thumb rule is to actually consider the total number of data points for the entire data set of the model, that is to be inversely proportional to the signal to noise ratio. Now if the large channel has SNR of 4 and a small channel has SNR of zero point 0.2, which was the case in our example here, you can see that it needs about 25 weeks of detection. Again, this is a rough estimation based on an assumption of a nonlinear model. Exactly, the nature of the model can be a little bit more complex, and I mean by model I mean the relationship between data requirement or the number of the sample size or the data points, whichever way you call it, with respect to sample to noise ratio. And the smaller channel will require almost 500 weeks or 10 years for detection. Again, this is an estimation, but with an SNR of zero point 0.2, that's pretty close, I mean, I would say, to that sort of a thing. And this is coming basically, or you can say that this graph is coming from that concept, showing that inverse relationship this time. So earlier we saw that with respect to R squared, SNR has a direct relationship, but with respect to data duration requirements, as you can see, as SNR increases, your data requirement actually decreases, and this almost feels like an exponential drop. And you can see that for smaller channels here, like we discussed, the SNR is much lower, and therefore you have a much higher data requirement. But for much larger channels, as you can see, as was the case here, like an SNR of 4, you can see that it corresponds to a much lesser requirement, only about 25 weeks, which corresponds to this horizontal line here at this point. So you also have middle channels and good channels, which just shows you some conceptual classifications. So the whole point here is that you need to take into account the effect of residuals. No matter how well you're going to model, there's obviously going to be errors, and the residuals are going to be there, and you need to take into account how that also affects the overall model fit, and how it affects the interpretability of all the channels. So if there are channels of different sizes and different kinds of variants, you might have to consider more data points, because the SNR is going to be not good enough with respect to model fit, and with respect to with respect to the variance. So you will really need to just get more data points. Sometimes that may mean doing hierarchical models also, so that you have simply more cases of the different variables, because you have more repetitions based on the different dimensions with which you're breaking down as per the hierarchical levels. But there can be different ways of doing this, but the easiest way is, if you have just 1 years of data, get 2 years of data. Okay, so signal to noise ratio therefore is incredibly important. Definitely consider it, not just while modeling, but even while deciding whether or not you should even do a model. Because otherwise, you can always run a model, but whether or not even it's going to be useful is something that really needs to be considered. And SNR is an important factor for this consideration. So hope this was useful. If you have any questions, as always, please leave them in the comments. Always happy to engage in conversations. And thanks for watching, and I'll see you in the next one.